Do you want me to keep my video on?
Yes, please. Good day, everyone. Welcome. I'm Jack Van Horn from the University of Virginia, and it is my distinct pleasure to welcome you to this edition of our 2024-2025 Foundations of Biomedical Data Science Seminar Series. Our unique lecture series is made possible through the generous support of the Integrated Translational Health Institute of Virginia, the University of Virginia's College of Arts and Sciences, the UVA School of Data Science, and through a grant from the National Institutes of General Medical Sciences. Since its founding in 2016, the Foundations of Biomedical Data Science Seminar Series has been at the forefront of exploring the transformative impact of data science methodologies, artificial intelligence, deep learning, and statistical modeling across diverse themes in biomedical and health sciences. Our selected theme for this year is focused on quantitative approaches in spatial multiomics for guiding personalized medicine, where every Friday we enjoy presentations from a wide range of leading thinkers about the issues, promise, opportunities, and hurdles associated with advanced genomic, transcriptomic, metabolomic, and other omic-related methods, along with a wide variety of data analytic opportunities which they present for data science, deep learning, AI, and spatial modeling. We are pleased to announce that our 2024-2025 application cycle is now open for our Biomedical Data Science Innovation Lab, and we hope that you or any of your junior faculty colleagues working in various areas of omics-related biology, as well as clinical medicine and statistics, will be interested in applying. Participants selected for our special Biomedical Data Science Innovation Lab program will utilize the content from the seminar presentations like the one you're going to see today as essential material for the culminating in-person manuscript and grant project development workshop to be held at the Hutton Hotel in downtown Nashville, Tennessee in June of 2025. We are very excited about this year's program where junior faculty biomedical and computational experts will come together to develop novel joint projects on the topic of quantitative approaches and applications for spatial multi-omic data types and their use towards guiding personalized medicine. For today's seminar, I am delighted to welcome our speaker, Professor Afsaneh Doryab from the University of Virginia. She is a BDSIL mentor this year, and she is a faculty member in the Department of Systems Engineering and in Computer Science right here at the University of Virginia. Her research lies at the intersection of ubiquitous computing, artificial intelligence, human-computer interactions, and digital health. Dr. Doryab focuses on developing computational models of human behavior using data from mobile, wearable, and embedded sensor data. She has received support from the National Science Foundation, from the National Institutes of Health, and her work has been published in esteemed computer science, engineering, and health venues all over the literature. In the spirit of our 2024-2025 Biomedical Data Science Seminar Series theme, Professor Doryab's lecture today is entitled Harnessing Mobile and Wearable Data for Personalized Health Insights. As mobile and wearable devices are increasingly capturing real-time health data, they offer very unique opportunities to transform healthcare through personalized insights. Dr. Doryab is going to explore for us today how model biobehavioral data from smartphones, fitness trackers, similar technologies can detect and predict health status and support tailored intervention. Sensor data analytics are proven very interesting as they have many affinities with the analysis of multi-omic data types as well. She will discuss methods and challenges for collecting that type of data, modeling it on physiological and behavioral patterns, as well as on how best to deliver strategies, leveraging these models for targeted interventions. And through case studies and recent findings, she's going to illustrate how this approach brings us closer to a proactive, individualized healthcare model, realizing the promise of precision health. As always, we are streaming this lecture live and for recording via YouTube. So if you're watching via YouTube, thank you so much for joining us. Also, our specially selected 2024-2025 Biomedical Data Science Innovation Lab participants and alumni are strongly encouraged to submit any questions they have via the chat feature in their YouTube sessions. I will synthesize these questions and ask them on your behalf during the last 10 minutes or so of the lecture today. And with that, thank you so much, Afsaneh. We are so excited to hear from you today.
Thank you so very much for the introduction. I'm delighted to be here. So I will jump into Just one sentence about my lab. This is the lab I run, Human AI Technology Lab at UVA. And as Jack mentioned, this interdisciplinary work in the area of HCI and AI and digital health. And I focus on modeling behavior from data streams. So for today, I focus on the applications of health using this passive sensing data. So basically, the three essential ingredients of my research in health domain are passive sensing, longitudinal data collection, and behavior modeling using AI and machine learning. I use these three ingredients to build predictive models to detect mental, physical, and social health and provide intervention. I have provided some examples of my work in this domain, although it was difficult to put all examples or all applications. I've worked on forecasting mood in bipolar disorder, which I will be talking about in a minute, predicting depression, loneliness, sleep quality, estimating symptom severity in cancer patients after chemotherapy, general behavior, healthy behavior, detecting implicit bias, friendship, and binge drinking that relates more to social health. But as I said, this area's health generally has a lot of overlap and it's difficult to distinguish between them. But I would like to I would like to mention that in all of these applications, I'm using mobile and wearable devices. And as Jack mentioned, the smartphone and wearable devices offer a rich set of sensing channels that makes it possible to track behavior and physiological signals. And they're also pretty unobtrusive and inexpensive, and people carry them around, particularly smartphone. So I would talk about a few examples where passive sensing has shown to be feasible in detecting mental health or health conditions in general. I would like to start with this case in predicting mood episodes in bipolar disorder. This is a very early work, and it's kind of an older work that I have done, but I would like to start with it because first, it is was among the first in our research community to show the feasibility of using passive sensing for health condition. And it also informed the trajectory of my research in the health domain. And third, also, it shows why personalization is so important in the health domain. So during my postdoc years, I was involved in a big European project called Monarca for monitoring and managing bipolar disorder. So as you see from this image of the smartphone, you see that this is an early smartphone versions, but the system was pretty advanced. It included actually the full loop communication between patients and medical care providers. The idea was to enable patients to monitor their own condition, and also the medical health providers to monitor and track the patient's conditions outside the lab setting. But why was this system necessary? So I'm sure you know about bipolar disorder, but it's a disorder that causes extreme mood swings. And if it is not controlled, the patient, there is a risk that the patient falls into the extreme episodes of mania or depression. Although the percentage of adults that experience bipolar disorder is relatively low, around 2.6%. However, 1 in 5 patients with suicidal thoughts and bipolar disorder commits suicide. So this is a disorder that really needs to be controlled and monitored. So current approaches for managing bipolar disorder are, of course, medication, but also psychoeducation, because each patient has different set of symptoms depending on which episode they are in. They need to be able to detect their warning signs and symptoms associated with them. That is particularly relevant for them. For example, one patient might, in their mania state, they might experience that they start living and they start sleeping in the living room instead of the bedroom. So, but for another patient, they might experience insomnia or other types of symptoms. So the idea is to train the patients to be able to assess their own behavioral patterns and symptoms. So I believe this is still the case, that the patients are given a paper sheet to track their own behavior patterns, activities, sleep quality, alcohol use, etc. The problem with this way of tracking is that, first of all, patients forget to fill it out. And they oftentimes do it like right before the therapy session starts. Also, depending on their condition, they might feel that if they're in mania, they might feel, okay, they feel fine and they don't need to do to track their condition. And if they're depressed, they might not even be able to have the energy to do anything. So the very first thing that we did in the Monarca was to replace the paper-based monitoring with a diary-based application, and the patients could basically put enter the quality of their sleep, medicine activity, etc. And they could also see the history of their symptoms. They could track their warning signs, and this information would be communicated with the clinicians as well. But so the problem was still there. So this worked fine for the patients to more regularly track their symptoms, but the problem was that if their conditions worsened or got better, they would stop using the app and entering the data. What we wanted to do was, or what we wanted to find out was if we could leverage mobile sensing data to automatically assess the patient's conditions and predict the mood of the patients, but we didn't know how feasible it would be. At the time, we had only collected self-reported data of mood, sleep, medication activity, warning signs, cognitive problems, alcohol, and stress. And so we decided to do a quick analysis to check the feasibility of this approach, to know if the data was feasible or predictive of any behavior in the patients. So we had at the time around 10 patients, and we asked them to rank the behavioral factors that based on the impact on their mood. So the patients ranked, for example, sleep as the 8 patients ranked sleep as the very first behavioral indicator impacting their mood, followed by activity, stress, etc. We didn't use the same data we had collected from the patients and used 3 algorithms to do the same ranking. And we were surprised to see that actually the rankings were pretty similar to what patients reported. So the 5 highest ranked parameters were mainly common. The main difference was that our algorithms thought activity was the main behavior factor that affected mood, followed by sleep, and it was the opposite in the patients. But that was a good sign. So we went ahead and developed a machine learning pipeline as part of the Monorco system, where we tracked sensor data from the mobile application, accelerometer, screen applications, call communications, and also self-reports. We processed the data, extracted features, and other types of processing. We use this data to predict the mood of the patients on a daily basis and identify the factors that affected their mood in the past and the factors that currently impact their mood. We also use time series forecasting to categorize the mood and forecast the mood categories 5 days ahead of time. We showed this information to the phone, to the patients, and also on the web portal, both to the patients and clinicians. So I quickly mentioned that the algorithms that we use for mood predictions were a combination of this tree-based regression, SVM, linear regression, and we also used the 3 algorithms that we had that I just showed you, chi-squared, information gain, and significance for ranking the behavioral factors. Also for forecast, we used support vector machine for regression and categorized the scores into depressed, neutral, mixed mood, and manic. So we also build an interface in collaboration with, collaboration with patients and clinicians. Particularly this, the application interface on the phone was a PhD student working with closely with patients, and it was a participatory design. I'm mentioning it because it was important, the more we build such applications, the more we realize how important the privacy considerations are for patients. And this application was actually designed considering those factors. So it was the concept of ambient displays, where it shows the behavior factors, so that like it appears on the front screen of the phone without actually revealing much information about health, but the patients themselves will be able to see a quick overview of their own condition. Like these bubbles had a color associated, like the color of the blue, for example, was sleep, yellow was alcohol, and purple was activity. And the direction of the bubble, and the size of it would indicate how big the impact of that behavior was on the mood of the patient. In this case, for example, was sleep. And the direction of the bubble would say whether it was the effect was in the past or it was current. So these 2 behavioral factors were in the past, and the activity was this current mood. And we would show also the effect of the percentage of the activity or the behavior factors, how much they affect the patient's mood. We showed the mood forecast only to clinicians on the web portal. And the reason was that we had a lot of discussions with clinicians about whether or not to show this mood forecast to patients. And their argument was that if you show the mood forecast to a patient who is already depressed and tell them, okay, they would be still more depressed in the next few days, they might become suicidal. And so that would be good news. So we decided to only show it to clinicians. But we ran a study, and we asked patients about their experience, and we found that impact factors we showed on the app informed patients about interconnections that they did not know existed and in their behavior. But sometimes they weren't sure how to interpret those signals or that information on the app. Clinicians were more cautious about the results of the prediction results. They used it as something to keep an eye on and reach out to the patients if necessary, but they relied on their own experience or expertise, which was totally fine with us. But so all was good. This pretty informative. However, we wanted to know whether the mobile sensing and passive sensing data could be used to predict the mood of the patient, or it was any, that had any value in this domain. So what we did was we built models using only passive sensing data to forecast mood, and another model using passive data and self-reports. And we found that passively sensed data provided nearly the same performance as self-reports. We had one anomaly when we checked, actually, this is with self-report data, and we saw that these patients did not have much variation in the self-reports. So so actually using self-report data was had more error than using only passive sensing data. So that was encouraging, and that was the first time we saw actually that passive sensing was feasible for detecting and predicting a health condition. So Monarca was actually a very successful project. It became the monitoring tool became commercialized. It's on monsenso.com. It's still being used by researchers and clinicians in several Danish hospitals. So I'm not involved in it because I moved. But what it did was it led to more collaborations. I'm still working on 2 other major projects for passive monitoring of symptoms in cancer patients and also managing adolescents' mental health. Both of them, we just finished a clinical trial and still working on that and the data. Just a little bit about mood ring, the same concept as Monarca, where we had a mobile app to passively sense and monitor the behavior of the teens and predict their mood, showing their mood to them on the app. We also had the parents involved. So we had, in addition to clinicians, we had the parent involved in the app so that they could actually see the results of the mood prediction, and they could also input data if needed. We had clinicians view to also monitor the teens outside of clinic. We had because we were running a clinical trial, we had a dashboard for monitoring the compliance of the patients and reaching out to them if data was missing and we weren't receiving data from the app. So the concept, as I said, was the same. However, we focused on different challenges in behavior tracking, including battery inefficient data collection, which is a problem. Of course, we want to have more sensor data, and the more data we have, the better predictions. But that is not really feasible because patients cannot really, it uses a lot of resources on the phone. So we had to find ways to actually collect less data and still be able to predict the mood more efficiently and more accurately. Related to that is missing data from sensors or self-reports for different reasons. as I mentioned before, the patient conditions might be a contributing factor, or users stopping to use the application, which is pretty common in our case for different reasons. And we, in order to basically lower the user's burden, we don't want to ask for self-report, which works as a ground truth in our case, but it leaves us with less data. We have a lot of sensor data, but we don't have much ground truth data. So that is a challenge to deal with. We have other problems like cold start problem, which is when we deploy an application, we don't have any data from the person to begin with, but we have to show the predictions almost from day one, or at least week one, or pretty early. At most, we have 2 weeks to keep the patients in the study and make sure they have confidence in the application. Otherwise, they would drop out and they stop using that. Also, there is a challenge whether we should use personalized or individual models, or use generalized models that uses data from the sample population. So we have sort of explored different methodology and different approaches with this in Moodring application, where we built models using population group and also building personalized models or individualized models. And we found that individualized progressive models perform best. So by that, I mean using data progressively. So if we deploy an application, you know that so we have the first week, we have only 1 week of data. The second week, we have more data. So we basically simulated or the same process that it appears in the deployed application, where we used data from the week 1 to predict week 2, and then week 1, week 2 to predict week 3, and so on. And we found that actually this provides better results. However, for the cold start, so the week 1, we wouldn't have any data. So what we did was to use the population model that we had from the previous patients. Given that they have sort of same condition, we thought to build a model and use it as a pre-trained model to begin with. We are still analyzing the data, but initial results show actually that it might not have the same effect because, again, each individual patient has a different behavior pattern, and using models from other people might not be quite predictive and useful in the case of individual patients. But so we will have more results coming up hopefully in the next few months. So I want to switch gears a little bit and talk about another area of research that is the same, using mobile and smartphone data, so smartphone and wearable data, but kind of relates to both health conditions and also general wellness, and is biobehavioral rhythms, which are repeated cycles of physiological, psychological, and environmental events in people's lives. And some of them you might know as sleep activity cycle or 24 hours circadian rhythm. So different environmental factors affect our biological and behavioral processes. Our biological and behavioral processes affect each other as well, and they have just a cyclic patterns. At least that is our hypothesis we wanted to test. So biobehavioral rhythms are associated with numerous health and life outcomes. And given that we can collect biobehavioral data using mobile technology in the wild, our question was, can we detect and model rhythmicity in human behavior via longitudinal passive sensing? And if we can, are those rhythms useful in predicting health outcomes? So we explored biobehavioral rhythms and using data from cancer patients to predict readmission risk after surgery. And so readmission risk is in cancer patients is high. Nearly a third of the patients are readmitted within 60 days. And there is a large and growing literature linking circadian dysregulation to poor health outcomes. So we wanted to explore to see how, whether or not we could model circadian regulation or disruption. So we analyzed Fitbit and smartphone sensor data from 49 patients who were undergoing abdominal cancer surgery. This data was collected in collaboration with clinicians at the University of Pittsburgh Medical Center. We modeled individual behavioral rhythms before surgery in hospital and 60 days after discharge. And we used the models, the features obtained from those behavioral rhythms in a machine learning pipeline to predict the readmission risk. But we first modeled periodicity or rhythmicity using these different algorithms for detecting cyclic behavior in the data, like cosigner, autocorrelation, and periodogram based on Fourier transform. And we ran these models on algorithms on activity and heart rate data from Fitbit. We identified circadian disruption before surgery, in hospital, and after discharge. And we observed significant differences in rhythms for all patients in all three stages. So, for example, if you look at these, the models for a non-readmitted patient, so let me orient you about what this graph is. So the blue line is the cosigner waveform. And the black line is the raw data. The x-axis is the hours and days before the surgery, and the y-axis is the average length of the activity bouts. So before surgery, the pattern is pretty normal, regular. In hospital is still regular, lower, different waveform and lower amplitude, but still normal. And after discharge, it goes back to normal. But if you look at this, the readmitted patient, the same model for readmitted patients, before surgery is also pretty normal, lower amplitude, but normal. In hospital is quite disrupted. And after discharge, still doesn't go back to normal. So we observed circadian disruptions in all patients, but the majority of the patients had a normal 24-hour rhythm before surgery and after discharge. But most patients had a disrupted rhythm in the hospital, and none of the readmitted patients had a normal 24-hour cycle in the hospital. This was an early sign that in hospital data might be actually good for predicting the readmission risk. So we use the cyclic features in the machine learning pipeline to predict readmission. The cyclic features in this sine wave include measure, period, amplitude, phase. We have a bunch of these list of these features we extracted. We used boosted logistic regression with an ensemble of linear regression and decision sum as base learners, and we used leave one patient out cross-validation for evaluating the performance. So we compared the performance with two standard methods for that is used in the hospitals called LACE and hospital. And all of our models outperformed this baseline, and particularly baseline measures, particularly in hospital data, had the highest accuracy and a recall of 65%, meaning more than 6 out of 10 patients, readmitted patients, were identified accurately. So that was a good starting case for using the feasibility of these circadian rhythms in detecting health outcomes. So confirmed that this can be the rhythms and cyclic behavior can be detected from consumer level devices like Fitbit and smartphone. And that those rhythm models can be used to predict health outcomes, here readmission risk. And this led to an NSF project for exploring more of the computational modeling of human rhythms. And we had more questions about, what type of cycles or rhythms are there, how often they repeat. So we only knew about the 24-hour cycle, but are there longer, shorter cycles? What sensing signals reveal information about those rhythms? So we knew we could, we obtained these signals, but the challenge was that different data sources of sensing signals might capture different aspects of the cyclic behavior. Like location or movement behavior can be captured by GPS signals and also Wi-Fi and Bluetooth. So all signals must be explored. But if we do that, it will result in a large number of models that makes it difficult to explore and interpret. So we needed to also develop more computational steps to be able to extract insights from those models. So this ended up being the work of my first PhD student who graduated last year. He developed a computational framework for modeling biobehavioral rhythms. We basically process the data rigorously from the sensing signals and building stationary and non-stationary models, detecting variation and stability in these models, building machine learning models, and using those models to predict different outcomes like mental health, productivity, etc., which, a couple of them I will be talking about in a minute. I will only focus on this, the top part. We have done a lot, and we are still analyzing and processing this data that we collected. So the pipeline for modeling rhythms is, it has this what I call standard parts for processing sensor data, cleaning, imputing, extracting features, but it also had the parts for modeling and the cyclic, processing the time series data, and detecting the cyclic waveform, and extracting rhythmic parameters or cyclic features, and using those features in modeling, in machine learning modeling, and model evaluation and performance. So the two case studies I will talk about where we use this framework. The first one is in college students' mental health. The questions we had in this case was, can we observe cyclic patterns in students' biobehavioral data over the course of the semester. If we can, are those patterns consistent, or do they change in different periods of the semester? Or do we observe differences in cyclic patterns of students with different mental health conditions? If so, do we see a more stable pattern among healthy students as opposed to students with mental health conditions? And how accurately the models we have built from rhythm features predict mental health status, particularly what cyclic features are associated with the health status. So we had smartphone and Fitbit data set collected from 138 students. The data set was collected at CMU, and we had collected this smartphone and Fitbit data throughout the semester, but we had only self-reported measures at the beginning, at the end of the semester. We collected like depression, loneliness, stress, resilience, and many different factors, but we only had 2 data points at the beginning and the end of the semester. The outcomes we looked at were post-semester depression, and we simplified it by looking at only the binary outcome, no depression or depression, and also loneliness, no or to low loneliness versus a moderate to high loneliness. At the beginning of the semester, depression, 14.5% of the students had depression, and this percentage increased to 40.6% at the end of the semester. So it's a high, significant increase. But loneliness had the opposite direction. At the beginning, 63.8%, at the end, 58.8%. And we think it was because we had freshmen students who probably weren't like that familiar with the college environment, didn't have friends and so on. So that's the reason for the trend and declining the trend at the end. We looked at the data and we processed it to model. We grouped the data into hourly beans because we wanted to see, we wanted to extract fine-grained features and model as the rhythms or cyclic behavior as detailed as possible. Extracted features related to mobility, activity patterns, communication, social interaction, and sleep, like travel distance, sleep efficiency, movement, intensity, etc. And we split the semester data into 14 days every 2 weeks because the university semester was 16 weeks. We divided it into 8 time windows. And we build cyclic biobehavioral models for each student and each time window. So we had a lot of models built as a result. We looked at the data. I'm just reporting for one feature, daily sleep duration. So we have we have a lot of these are a sample of what we could do with using data from obtained from these models. So we saw for sleep duration, most students maintain regular daily sleep duration. So in this diagram, you see pre-1, post-1 means students did not have depression throughout the semester. Pre-1, post-2 means students did not have depression at the beginning, but had developed depression at the end. Pre-2 had depression at the beginning, but no depression at the end. And pre-2, post-2 means they had depression throughout the semester. So we only see that the ones who actually had depression throughout, they had the most disrupted 12-hour cycle. And so 12-hour is associated with diurnal and nocturnal cycles. So it looks like that they had actually more irregular sleep duration at night. We also saw lower regularity in sleep duration, students that developed depression at the end of the semester, but did not have depression or loneliness at the beginning, but they had it at the end. And you see that this regularity in the patterns decreases in both pattern, particularly in the 12-hour cycle. And this deep is in time window 4 is when the spring break happened, and we see a little bit of different pattern associated, which is understandable or intuitive. So besides that, we wanted to also understand how accurately we could use these cyclic models to predict depression or loneliness. So as I said, we extracted this rhythmic features from this from the models we built and used them in the machine learning models for training. We built a lot of models from a combination of sensors and time windows, and we only reporting the ones that outperformed the majority class baseline, and the prediction was above that baseline, but still there were a lot of models produced. So I just give you a very summary of some of the results. So we had we looked at the models that were built using rhythm parameters and the models that did not use those parameters, only used raw sensor data. And we saw that all of the models that used the rhythm parameters actually outperformed the ones that were built using only raw data. And this is only showing the results for loneliness, but this was the case for all models. And you see, I'm also only showing the representative features for each time window during the semester, but this was pretty much the case for all features. So this case was only using one semester data among students, but we also wanted to know whether there were longer cycles than one semester. We had physiological data from 11 volunteers over several months who wore the Oura ring, and we used that data to do the modeling and see whether we could detect longer cycles. We aggregated data into daily intervals for this case, and again detected significant periods and cycles, and predicted readiness scores that is shown by the Oura ring as the ground truth. We saw near weekly cycles in the activity, sleep, and heart rate data. As you see here, activity particularly seems to have like less than a weekly cycles. But sleep is mostly weekly. Skin temperature was bi-weekly. It was interesting that it was a bi-weekly cycle that we observed. So would be interesting to look at more data from other, for example, Fitbit, to see if we can see the same cycles and with other participants. So, but this is for further exploration. It was still interesting to observe this for the first time. We also saw that variability in the rhythms was highly predictive of the readiness score. So you see these the features that were frequently appearing in the models were standard error of each feature. So measure standard error, amplitude standard error, and phase, etc. And the standard error is associated with the variability in the compared to the feeded in raw data compared to the feeded model. And so that was a sign of variation to be predictive of readiness. We also saw the combined sleep, calories, and step were predicted readiness with lower error. So I'm just wrapping up and saying that this again, we're continuing doing this because we have a lot of data we have collected and we're just processing and doing the modeling. But I want to conclude with just a few of the challenges that remain, that our models predictions are limited to what devices can sense. And some, if the device cannot sense the certain behavior, we won't be able to extract insights. So this is from the work we've done in personality detection. And we realize that deep and complex behavior cannot really be detected or confirmed with few sensors. We also see that more and more limitations are applied to the data we can collect from smartphones and wearable devices. These are phone companies for different reasons, privacy and lack of trust in technology, etc. So it will be interesting to see how much we can do in the future. We have shown the feasibility. I showed, like few successful cases, but the more restricted the data access gets, the more challenging it becomes to actually extract insights from such data. But it will be interesting to see. I mean, we are working on doing, like using less and less data and see how much we can actually detect still and predict model behavior accurately. So with that, I just conclude my talk and thank you for your attention.
Afsaneh, thank you so much. I really appreciate you sharing this because these topics have so much to bear on how we personalize people's health, their personal behaviors, their activity, their mood, their basically physiological parameters. And it might seem a little bit odd that we're having you talk about sensor-related data when our theme is on multi-omics guiding personalized medicine. But the thing about it is that a lot of the same challenges seem to exist in both spaces. And it might seem a little bit unusual at first to think about it that way, but I really think it does. You mentioned one in particular, being able to geolocate people using, say, their smart devices. Basically you've got people moving around in space. Well, chromosomes and the genome is basically arranged as a spatial arrangement of things, and being able to do statistics in space is super important. You also mentioned something which I think is a common thing which happens across all different data types, and that's of missing data and how you handle that. And I was curious if you might firstly comment on the notion of how modeling, the types of modeling you're doing with multivariate data types in this space might have affinity for what's going on in, say, multi-omic related data. Now, realizing, of course, you're probably not an overall expert in that, but that you've got expression data, you've got, genomic data, you've got various other omic type datas that are all in this kind of space, layered on top of people's behavioral, physiological, and other data. How can we, one, learn to analyze data in each of those domains, but also bring them closer together to personalize people's health? And where data are missing, how can we kind of impute between all these things? And is that even helpful?
Well, that is a very interesting, also still challenging question. It's we have been trying to do to handle the problem of missing data. I wouldn't. So we have had different strategies. I won't be able to claim that we have figured it out, to be honest with you, because it is very challenging. So our challenge is that we have people using these devices in the wild, what we call in the daily setting, and for different reasons, people, we miss the data. Sensor is not working. People don't want to turn off the sensor, etc. So that is the reason we don't get the data we need. But that is the reality. I think it might actually be a little bit more stable when it comes to genomic data, behavioral images, medical images, and etc. Because those are taken in certain situations, certain condition, and but it is still possible that for different reasons the quality of the data is not as expected, and we still end up with having to remove the data. I would say what we have found to work relatively well is that using the person's own data for imputation works better. The risk is of course that we might inflate the same type of data, so the model would be basically biased with the same data, and we might lose some of the variation that we could observe. But it will fix the missing data, and we will have more data points. We have, as I mentioned, we have also used data from other people, billing model from other people as a way to handle the missing data for a particular person. And that has, in our experience, that has not helped. So it basically results in less accurate models. So that's basically highlights the individual behavior, the individualized aspects of these models that needs to be taken into account. I don't know if I answered your question, but
Well, I suppose, in the context of having the multi-omics data, having that as almost, you could think of it as like a prior, or it's just additional information which may contextualize somebody's biobehavioral data. Obviously somebody who, for example, you mentioned some folks who you've analyzed that have cancer. All right. Obviously, cancer is not a happy thing usually, and so mood may be more variable in people who have cancer. So being able to look at just I don't know, the multiplexed amount of data from people, say from clinical conditions like that, maybe that would be, there may be some strategies that you might envision for how best to do that. I'm just kind of curious.
Multimodal data would definitely be helpful.
Yeah.
My hunch is that it's just basically it captures different aspect of the person's behavior. Sometimes you can get the insights from one modality. Rarely it happens. So oftentimes in our work, we have found that the combination of different modalities would provide best insights. And as I mentioned, like you capture the behavior or the state of the person from different sensor data. And so I assume it would be the same for each type of condition or outcome we're looking at. So I don't know like what case could be cancer patient, like where we have test results and the health conditions in the hospital, and
I
medical.
guess I'm just kind of wondering if, again, this is just another type of omic data. I know it's
Yeah,
not genomic data, it's not metabolomic data. It's kind of behavioral omic data, if you will, because you're potentially capturing so many things about how somebody moves through space, about how you're tapping into their mood, perhaps other physiological variables. And it's just all part and parcel of this overall personalization of medicine that
yeah,
we're
yeah.
so interested in trying to tap into.
Yeah, so this data, the data that I work on is just basically captures variations in the behavior. So the genomic data, supposedly, I think there are variations there too. I don't know enough about that, but the biobehavioral data is very variable. So one day you have a better mood, the other day you don't, you're in bad mood. It might be caused by a certain physiological condition or physical mental health condition, but that's variable. So that's what we look at. It's not a static data, is variable data. And I think it can inform the underlying physiological and mental health conditions, but it can also cause some of these conditions. So in other words, I do believe that the multimodality of the different type of data would be very informative. It's best to use this multimodal data um, in different conditions. Different data sources would be helpful depending on what outcome you look at.
Well, I think it's all very exciting about how we think of omics in this very large, kind of broad definition. So it's not just of some genomes and or RNA-seq of gene expression or what have you, that actually encompasses the entire individual. And
Yeah.
that's why I think this is really exciting. So I do see connections here, which I'm very excited to tap into. But we're at our time. So Afsaneh Doryab from UVA School of Arts and Sciences, thank you, or sorry, School of Engineering. Thank you so much for joining us. Thank you so much for sharing your work. We look forward to further interactions with you as one of our BDSIL mentors. Have a wonderful weekend, and everybody who joined us, thank you again and have a wonderful weekend. We'll see you soon.
Thank you so much.